Sure, thank you. Thanks a lot for the invitation and putting together this nice meeting. I'm really enjoying it. So today I will speak about the recent work this year, which is done with Andreas Koch and Hao Yusung from UT Austin. I will focus on the ADS3 CFT2 duality where the gravity is in the strongly coupled regime. And on the field theory side, we have the minimum model CFTs, in particular the Ising CFT. I will review the status of duality studies in this strongly coupled regime, and then especially concentrate on the case where a genuine boundary is present in addition to the asymptotic boundary. I don't have a lot of slides, so please feel free to interrupt, discuss, and help me fill in the 70 minutes. Okay, so I'll start by several pedagogical slides to the ADS3 CFT2 duality. So here are some basics of three-dimensional ADS space. This is the Einstein. So here is the Einstein-Hilbert action. R is a Ricci scalar and lambda is the cosmological constant as usual. In 3 dimensions, simple counting of degrees of freedom shows that the Riemann tensor can be completely determined by the Ricci tensor, and namely there's no traceless part. From this, one can show that in a vacuum without matter, the solutions of Einstein's equation have a constant curvature. Physically, it means there are no gravitational waves classically and no propagating gravitons in the quantum theory. Furthermore, the static masses do not experience Newtonian gravitational force. This makes the 3-dimensional gravity sounds rather trivial, but black hole solutions can still be found with event horizons and expected thermodynamics. However, there's no singularity at the origin. One more thing is that the 3-dimensional gravity with negative cosmological constant can be viewed classically as a double Chern-Simons theory with the following gauge group. By double Chern-Simons theory, I mean 2 copies of Chern-Simons theory with SL2R gauge groups, but with opposite levels. The foundation of ADS3 CFT2 duality was laid by the work of Brown and New back in 1986, which shows that the asymptotic symmetries that preserve the asymptotic metric of ADS3 form 2 copies of the Virasoro algebra. And in particular, the results lead to the identification that the central charge of the Virasoro algebra is equal to 3L over 2G, where L is the ADS radius and G is the Newton's constant in 3 dimensions. So there's a more mathematical perspective of this ADS3 CFT2 duality. Roughly, it says that there is a 1-to-1 correspondence between the hyperbolic structure of a 3-manifold M and the conformal structure of its boundary partial M. Okay, however, despite a seemingly simple theory of ADS3, despite the beauty of Brown and New theorem and a lot of efforts, the ADS3 CFT2 duality is still not well understood. The field theory due to the pure ADS3 gravity is still unknown. There have been proposals that the pure gravity should be dual to Liouville CFTs, extremal CFTs, etc. But all proposals have different kinds of problems and subtleties. More recently, the exciting possibility of ensemble average CFT duals have also been discussed, as we have heard from Professor Guli today, but they have not been studied yet in the context of pure gravity. Most of the studies so far have focused on the case of large Brown and New central charge, namely the weak coupling limit. Formally, we can write the gravitational path integral in this way. We will always work in the Euclidean signature in this talk. We'll fix the boundary condition to be that of a 2-dimensional torus, which is the simplest possibility in Euclidean signature. The Brown and New central charge shows up as a prefactor. Thus, when it's large, one can do the saddle point approximation in this semi-classical limit. One can rewrite this path integral as a sum in this way. The X are the 3 manifolds where the gravitational theory live in. Semi-classically, each X corresponds to a solution of Einstein's equation. And there are also fluctuations around these saddles, which are included in this C of X. The tau and tau bar are the modular parameters of the boundary torus. So the semi-classical treatment, however, already imposes a series of issues. The first is a relatively minor one, that the perturbations around the saddle point solutions are not easy to compute. And yes, there are results based on the heat kernel method, Zhu-Xi localization, coinjoint orbits, etc. at 1 loop level, but they're not easy. And if one goes to even higher loops when boundaries of higher genus, then the calculations become too complicated. So we have a not so happy case here. The second issue is that the summation over contributions of different saddles is badly divergent, even if we fix the boundary condition to be just a torus, and regularization is required. Well, this makes the result not so nice looking, but it's still not so unusual, especially for gravitational theory. The next one, however, is more serious. Recall that the Brown-Liu result says that the symmetry group relevant to general relativity with asymptotically ADS3 boundary conditions is 2 copies of Virasoro algebra. This means that the partition function of d of x must be the character of some representation of Virasoro algebra, or in other words, a canonical ensemble partition function at fixed temperature and angular potential. However, the result of Maloney and Whedon in 2007 is that the summation over x cannot be written as such a trace for any commuting operators H and J in Hilbert space. So now we are really unhappy. Or still, when one writes the partition function as a sum over different energy levels and angular momenta, one finds that there are negative density of states. Namely, this F can be negative beyond certain E star. Interestingly, and maybe surprisingly, in the strongly coupled regime where the Brown-Liu central charge is of order 1, or when the ADS radius is a Planck scale, this problem seems to be absent. So this was due to the, yes.
May I ask a simple question? I cannot understand how this C appears in the exponential. Can you simply tell me that you make a path integral, I understand, over the matrix and this the Euclidean actions, but why this C appears there?
Oh, it's not so. This should be understood as the dimensionless coupling constant 3/2g. So it's a purely a gravitational quantity. So
and if you want to semi-classically study, so it will play the role as some perturbation parameter or something later.
Yeah. So when you do the expansion, it will be like SE of order 0, 1 over C plus S of order 1. Sorry, order 2, because instead of point, there's no order 1, etc. So let's see is the parameter. And 1 over C is a small parameter. Yeah.
And when the negative density of a state becomes negative, it is reminder me the case of the ADS2. When you have considered the gravity in ADS2, the jetty gravity, then also the density of a state becomes negative. So, and the proposal, as you know, is that the CFT dual is not only a single quantum, so it's an ensemble of some matrix model. So is it the case here also? Did somebody study the dual of ADS3 as an ensemble of some matrix models or some things? Just I'm curious to know because.
Yeah, that might be a solution. Yeah, and as I mentioned, there have been exciting explorations of ensemble averaged CFTs at field series due to the gravity. This is also related to Professor Goulet's talk. But this aspect of the problem is not will not be explored in my talk. So I will be focusing in a case where there is only one. So I'll be focusing on the Ising CFT case. So at C equals 1/2, there will be only one CFT. So there's nothing to average over. Okay, yeah, but yeah, in general, an ensemble average CFTs could be a possibility to resolve this problem.
Thank you very much.
Thanks for the question. So yeah, I was saying that interestingly, or yeah, maybe surprisingly, in the strongly coupled regime where the Brown-Liu central charge is of order 1, and or when the ADS radius is a Planck scale, then this problem seemed to be absent. And this was due to the pioneering work by Castro et al. The partition function of quantum gravity was computed rather easily in this case. It's not a direct evaluation of the Euclidean path integral, though. It uses certain assumptions and arguments, which we will briefly review later. And also it has invited a lot of questions and puzzles, well, which is typical for interesting works. So we will focus on the Brown-Liu central charge smaller than 1 case and consider the possibility of the dual theory being minimal model rational CFTs. We've seen that in this regime, based on the work by Castro et al., that the gravity theory is free of many problems. And more importantly, strongly coupled gravity is obviously interesting. And the minimal model CFTs have been well studied in statistical mechanics, condensed matters, physics, and mathematics. And given the simplicity of these theories, the duality, if fully understood, would likely shed light on the nature of holography and the emergence of geometry from quantum field theory. And also from a technical perspective, the TQFTs, topological quantum field theories corresponding to these CFTs are also well understood. And one may use this method from TQFTs to approach the problem. And so Castro et al. Showed that when C is smaller than 1, and when the asymptotic boundary is fixed to be a torus, the summation over X turns out to be finite. And the partition function is simply a constant prefactor times the minimum model CFT partition function. And the central charge of the CFT will be equal to the Brownian central charge in the gravity. So what we'll do in this talk is to add a genuine boundary to the system in addition to the asymptotic boundary. It's a natural question to consider that what additional information can enter the duality story when a boundary is present. The field theory that lives on the asymptotic boundary would be boundary CFTs, BCFT. It has many connections with different branches of physics. For example, deep rings in string theory, the study of topological phases in condensed matter theory, boundary critical physics in statistical mechanics, and also quantum impurity models, quantum dots, etc. And most importantly, of course, in holography. So, and the bulk theory has to be augmented with Randall-Sundrum brings. It's known that the Randall-Sundrum brings with tensions can be used to smoothly truncate the bulk spacetime in order to yield the geometry dual to a CFT with genuine boundary in the semi-classical case. The ADS BCFT duality has been studied in semi-classical limit, which we'll review later. We would like to see if they are to be extended to the quantum regime, then what their implications would be. So next, we will move on quickly to review about the work on the duality between strongly coupled gravity and minimal model CFTs when a genuine boundary is not present. The method and details will not be used in our work, but I will still show the main logic just for the sake of completeness. So if you don't fully follow this part, it's okay, as I'm deliberately omitting things. The only thing you will need to understand our work later is their conclusion that the gravity partition function matches with the minimal model CFT partition function. Okay, so previously we have rewritten the Euclidean path integral as a summation of z of x over x, where x are the smooth solutions to the Einstein's equation. Now in the quantum regime, there is really no small parameter, and therefore it's improper to calculate the partition function as saddle point contribution, one loop contribution, higher loop contributions, etc., because the corrections are not necessarily small and are not controlled. However, in the reference, it's assumed that the partition function can still be organized into summations over classical saddles and potentially large fluctuations around them. I have to say, there's no established claim that topologies that do not admit classical solutions will not contribute to the path integral. But there is no known method to evaluate their contributions. Therefore, this assumption basically means that only known contributions to the Euclidean path integrals will be considered. Okay, anyhow, the assumption is made, and since the fluctuations are large, one cannot compute them order by order. This z of x must be obtained in one go, namely as a whole. So the different saddles correspond to different interiors or fillings of the two-dimensional torus and are related to each other by SL2Z transformations. To be more explicit, the partition function of one saddle can be related to the partition function of other saddles by these fractional linear transformations on the parameter modular parameter of tau. This ABCD belongs to SL2Z. The full gravitational partition function must be modular invariant and can be written as a sum over different gammas that belongs to SL2Z acting on the partition function of one saddle. This one saddle can be chosen to be any saddle. Natural one would be the vacuum saddle, corresponding to the thermal ADS3 solution to the equation of motion. The metric of the thermal ADS3 looks like this, with the Euclidean time going along the longitude of this solid three-dimensional solid torus. And there are two additional space dimensions along the meridian and the radial direction of the solid torus, respectively. So this is the dominant saddle at low temperatures. And this ZVAC is then argued to have the form of chi-vac norm squared, where chi-vac is the character of the vacuum conformal block of the Virasoro minimum model CFT, whose expression and the properties under SL2Z transformations are all well known. The argument is based on the Brownian result, and the main assumption is unitarity. And roughly, the logic is that we know from the Brownian result that the states of the gravitational theory are organized into representations of the local conformal group, the essentially extended local conformal group. This statement follows from the symmetry structure of theories of gravity with asymptotically ADS boundary conditions, and therefore should be true even in a strongly coupled regime where C is of order 1, or even C is smaller than 1. But when C is smaller than 1, the representations of the conformal group are highly constrained. We know, for one, that the possible central charges are already discrete. And also the number of irreducible representations of the Virasoro algebra is also finite. And in particular, this function dvac is then constrained to be the vacuum character of the minimal model. Okay, after establishing this dvac, one can then repeatedly act on the generators of SL2Z to find a closed set of partition functions that contribute to the modular sum. And as an example for C equals 1/2, this modular sum gives 8 times the Ising CFT partition function. So nobody knows what this 8 means. In the original paper, it was argued that this 8 can be absorbed into the path integral measure. I personally tend to believe it had some meaning. Well, it certainly had some mathematical meaning, but physically nobody knows. Maybe it means the gravity is 8 copies of Ising CFT. Maybe it means it's D8 times Ising CFT, or maybe this 8 really has no meaning. But this would require further studies. For other central charge values, for example, for C equals 7/10, which is the next simplest minimal model, the gravity partition function turns out to be some other number times the tri-critical Ising partition function. However, for C larger than 7/10 and smaller than 1, there are other subtleties and the duality cannot be similarly established. The difficulty is related to the existence of multiple modular invariants in the minimal model CFT. This probably means, as mentioned by Hiroshi and the previous question, that the field theory dual may actually be a combination of different CFTs. And unfortunately, I don't have additional comments regarding this question in this talk. So the previous results are based on the choice that the symptotic boundary is a 2-dimensional torus, namely it's a surface of genus 1. However, we know from conformal field theory that higher genus partition function could encode information about higher point correlators. So to recover the full information of the CFT, one needs higher genus partition functions. On the gravity side, higher genus on the symptotic boundary means multiple-sided Euclidean wormholes. So to really establish the duality, it would be nice to consider the symptotic boundary to have more non-trivial topology, namely to have higher genus. For the case of Brownian central charge equals 1/2, it turns out that the duality can be safely generalized to the cases where the symptotic boundary is of arbitrary genus. This is a work done with Chaoming Jian, Andreas Ludwig, Haoyu Sun, and Zhenghan Wang. We showed that the contribution of handle bodies to the gravitational partition function is still proportional to the Ising CFT partition function on the surface of higher genus, and this constant prefactor is finite. The main method we used was topological quantum field theory techniques. The tri-critical Ising case of central charge 7/10, however, cannot be easily generalized to higher genus. The problem lies in that the prefactor being infinite, and there's no natural regularization. Recently,
excuse me, is a result for arbitrary high genus, is that the new result?
It's the old result.
Oh, it's the old result? Okay.
Yeah, it's published in JHEP last year. Yeah. So that result was only for handle bodies. And recently, we have also been thinking about non-handle bodies as well. And we found these solutions can be described using surgery. And I will discuss more about this after finishing the main topic of the talk, if there's additional time. So the main focus of the talk, as mentioned earlier, is to see what can be learned from the conjectured duality in a strongly coupled regime when genuine boundaries are present. To this end, we have to review yet another thing, the semi-classical version of the ADSB CFT duality. Some useful knowledge of boundary CFTs are in place. When there is only one boundary component, the surface can be conformally mapped to just the upper half plane. So more interesting is the case with 2 boundary components, namely a cylinder or annulus. The partition function in the annulus case can be written as a theory defined on a circle of unit radius propagating over a finite Euclidean time 1/delta between initial and final Carty states labeled by A and B, where delta is a shape parameter of the annulus. So the partition function is a matrix element. And in comparison, the partition function in the cylinder case is a trace. It can be written as a finite temperature partition function of the theory living on a unit interval with inverse temperature beta equals delta. Here for the cylinder, chi of h is the Virasoro character of the irreducible representation of highest weight h, which corresponds to the primary field of conformal dimension h, and q is negative pi delta. This n, a, b, h are non-negative integers, and we will fix the value of this soon. So the conformal symmetry would require the 2 pictures to have the same partition function. Okay, let's see what the conformal boundary states, the Carty states, look like. The conformal condition for a circle requires that the boundary states should satisfy this equation, where LNs are the generators of the Virasoro algebra. And furthermore, recall that the full Hilbert space of the CFT can be decomposed into highest weight representations of the Virasoro algebra labeled by weight H, which corresponds to the conformal dimension of the primary fields. The small n's are again non-negative integers, so the conformal boundary states will be linear superpositions of states from VH tensor product V bar H bar. For diagonal minimal models, when n H bar is equal to delta H bar, the two requirements above lead to a unique solution for the conformal boundary states. These states were introduced by Carty and therefore called Carty states. So their specific form is the linear combination of Ishibashi states H. And Ishibashi states are defined as follows, where capital N is the level in the subspace V of H here, and J goes from 1 to the dimension of the subspace at level N of V of H. And the coefficients this can be solved using the fact that the cylinder partition function and the annulus partition function should be equal. The Carty states does have the following expression. They can be completely expressed in terms of the modular S matrix of the CFT. And the Carty states are in one-to-one correspondence to the primary fields of the CFT. And furthermore, one can also find that the small n's in expression for the cylinder partition function that we have seen before are just the diffusion rule coefficients of the CFT. And next, I would like to introduce another concept called the boundary entropy. Taking the annulus or the matrix element picture of the partition function at low temperatures when delta is small, only ground states labeled by zero of the Hamiltonian contributes. One can then use the usual way to compute the thermodynamic entropy, yielding two decoupled contributions from the two boundaries in addition to this bulk contribution. This GA or GB are called boundary entropy of the corresponding conformal boundary. And specifically for diagonal minimal models, these G's can be expressed in terms of the modular S matrices. And now we turn to the gravity side. The semi-classical version of ADS-B CFT suggests that the bulk dual of a B CFT is a gravity with branes. And here is the action of a gravity with a brane. R is the Ricci scalar as usual, lambda the cosmological constant, and we allow multiple boundaries labeled by small a, so we sum over them. K is the trace of the extrinsic curvature of the boundary, while TA is the tension of the brane. We will assume that the boundary matter is uniform, such that the tension is just a constant. And we take the following form of the metric. Note that this is a general expression that works for any dimensions, not just 3. When there is no genuine boundary, this rho will go from negative infinity to positive infinity. But when a brane is present, rho is cut off at some value rho star. In 3 dimensions, the symptotic, here's a figure. The symptotic boundary is the blue surface, and the genuine boundary is the green surface, while the 3-dimensional bulk is the region between the two sheets. And imposing a Neumann boundary condition, one can do the variation of the metric and find the equation of motion to be of this form. So it relates the extrinsic curvature to the brane tension. And one can then compute the tension using the expression of K, arriving at this expression. So now I'm going to introduce the ADS-B CFT basics. When the B CFT lives on a disk, namely when the boundary of the CFT is a circle, here, semi-classically, the corresponding bulk theory can be found to live in a part of the 2-dimensional sphere, as sketched in this figure. One can easily evaluate the gravitational partition function in this domain and compute its thermodynamic entropy. The subleading contribution is then the boundary entropy. So using the equation of motion from our previous slide, one can relate this boundary entropy to the brane tension in the following way. A more non-trivial topology is that of the cylinder. There are 2 geometries with branes that can realize a cylinder on its asymptotic boundary. The first is that of a thermal ADS3 that we mentioned earlier, which without genuine or real boundaries is just a solid torus with Euclidean time again going along the longitude of it. The other is the BTZ black hole, which without real boundaries is also a solid torus, but now the time is the contractible cycle, the meridian. Both geometries are locally ADS3 and only differ globally. And in both cases, the CFTs live on the bounding torus T2. And now we add the branes. For thermal ADS3, the only way to have a constant brane configuration in the bulk is what I call a bagel cut. The 3-dimensional gravity lives in one of the two parts of the bagel. The two parts don't necessarily have to be equal in size or shape. To understand this better, we can take a constant time slice, which is the blue disk here. Originally, without real boundaries, the CFT lives on the symptotic boundary S1 of the disk. And when the brain is present, the BCFT will live on a part of this circle, namely an interval, with two open points labeled in green. So there is only one brain smoothly connecting the two open points of the interval in the bulk, because the Randall-Sundrum brain needs to smoothly truncate the bulk spacetime and cannot end in the bulk unless it's wrapping a contractible cycle. Were there two brains, they would have to end in the bulk, and there's no contractible cycle to wrap. So that's impossible, and we only have one single brain. And since we only have one brain, then the two boundaries connected by this brain must have the same boundary condition on the BCFT side. For the BTZ black hole geometry, however, we can have a disconnected configuration with different brains ending on the two ends of the interval. Again, look at the constant time slice, which is an annulus here. When real boundaries are present, we think of a part of this annulus like this. And now there can be two brains, each wrapping the Euclidean time direction contractible in the interior of this solid torus. And these two brains don't have to be connected, and the BCFT side can host the different Carty states. Okay. The explicit solution for the two geometries have been found semi-classically by Takanagi and collaborators. The total action for the thermal ADS3 case turned out to be just this pi c delta over 24. And interestingly, the contribution from the brain cancels. And the action for this solution is independent of the brain tension, or in other words, it's independent on which boundary condition one chooses, as long as the boundary conditions are the same on the two boundaries of the cylinder. This feature agrees with the behavior of boundary entropy of the two-dimensional BCFT on a very long cylinder. Recall that very long cylinder corresponds to the low temperature limit on the CFT side. And on the gravity side, the thermal ADS3 solution also dominates in the low temperature long cylinder limit. So everything is consistent. For the BTZ black hole solution, the total action turns out to be of this form. There's again a bulk contribution, two decoupled terms corresponding to the two boundaries. And you may still remember this result from the BCFT calculations. The thermodynamic entropy there also contains a bulk contribution, pi c over 3 delta, and two decoupled terms from the boundary. So the gravitational calculation by Takanagi and collaborators satisfy this form that we found in BCFT. Now one can match the contributions of the two subletting terms with the boundary entropy. Okay, and now we have reviewed everything, and we can head for the duality with genuine boundary in a strongly coupled regime. In particular, we will focus on the case of the Brownian central charge equals 1/2. I would like to give a preview of if the duality is true in a quantum regime, then what predictions one can make on the gravity side. We will use the example of a disk to illustrate. We have seen that at the semi-classical level, the ADS-BCFT duality suggests a relationship between the brain tension and boundary entropy. If the proposed duality is also true in a quantum regime, then a similar relation like this should also hold. And using the boundary entropies of the Ising BCFT, one can instantaneously identify the allowed brain tensions to be negative hyperbolic tangent 6 log 2 or 0, corresponding to the three different Carty states or the three primary fields in the CFT. So the brain tensions can only take these discrete special values when the Brownian central charge is 1/2. Now that we have seen the main prediction, we will come back and check whether the ADS-BCFT duality in the strongly coupled regime can pass some consistency checks. We will study the cases with two real boundary components. And first, consider this low temperature limit. The gravitational path integral was computed in a semi-classically as mentioned, and can be rewritten using the parameter Q, which is exponential negative pi delta. On the BCFT side, the partition function of Ising BCFT is well known. One can do the low temperature small q expansion to see that the ZAB is exactly the same form. So it seems that although we're using the semi-classical results on the gravity side, there's still a beautiful match in the low temperature limit. Okay, now we move on to the high temperature limit. The semi-classical gravitational result can be rewritten in terms of another parameter Q tilde defined in this way. And we have also defined some G prime just to make it convenient to compare with the BCFT results later. On the BCFT side, at high temperature limit, this the Q is no longer small, so one cannot do the small Q expansion of the partition function. So we will perform a modular S transformation and do an expansion in Q tilde instead. One then observes that the results on both sides again match in the high temperature limit, as long as one identifies G prime with G. This is the same requirement as what we predicted in the disk case. That is this relationship between boundary entropy and brane tension. More comments are in place. We have examined the high and low temperature limits, which correspond to the thermal ADS3 and the BTZ black hole settles. But to reproduce the full partition functions, we should also take into account the fluctuations, which could actually be large. However, we can go through a similar argument as in the case without boundaries and find that the Virasoro symmetry is actually highly constraining, and the partition function has to take the form of combination of characters. Then in this combination, the weights or the prefactors are fixed by the high temperature and low temperature limit results. So one can expect that if one takes into consideration of the fluctuations, one will reproduce the full Ising BCFT partition function. And therefore, we conclude that the ADS BCFT duality can be extended without paradox to the strongly coupled regime of C equals 1/2, as long as one identify the boundaries entropy in the BCFT side to the brane tension in this way. Okay, and next, I will give some remarks on the general minimum models beyond C equals 1/2. The gravitational results on low and high temperatures remain the same, while the BCFT side will have these general expressions. They will match if the tension satisfies this box equation, namely the tension is fully expressible in terms of the central charge and the modular S matrix of the dual BCFT. This means that adding genuine boundaries does not impose further constraints to the ADS CFT duality in the strongly coupled regime. What else can one learn from the ADS BCFT duality? One prediction is the property of the gravitational partition function under modular S transformation. For the BCFT partition function ZAB with boundary conditions labeled by A and B, modular S transformation can turn it into a linear combination of ZCDs. After some algebra and application of Linde formula, we can solve for the coefficients in front. So this F ABCD looks like this. As an example, here I show that in the Ising case, how Z00 can transform. And it's rather complicated. So if the duality of ADS BCFT is true, then the gravitational partition function is always equal to the BCFT partition function. Consequently, this same expression describes how gravitational partition function with certain brane tensions are related to gravitational partition function with other brane tensions. And note, we have only modular S transformation, but not the modular T, because we only have a cylinder instead of a torus, and the T transformation is not really well defined. And similarly, there's no concept of modular sum either. Okay, and now let's summarize on this part. We showed that the ADS CFT duality in a strongly coupled regime of sims smaller than 1 can be generalized to the cases with real boundaries, and adding boundaries does not impose further constraints. That is to say, it does not constrain which minimal models can be dual to pure ADS3 gravity, unlike the case without genuine boundary. Then we find that the brane tension can be expressed in terms of the data of the CFT. Okay, and natural future directions would include adding more boundary components to the system, where more data of the CFT are supposed to enter. For example, the data about crossing symmetries, or mathematically what we call the F symbols. We can also consider the defect CFTs, which generalize the notion of a boundary. One can use the folding trick to reformulate an interface as a boundary. But then even on the CFT side, the classification of interfaces are much less understood, because the CFT now becomes, for example, in the Ising case, a theory of Ising times Ising bar due to the folding. Another possible generalization is to go even further and consider interfaces between different CFTs in the field theory side. And on the gravity side, this would correspond to spacetimes with different cosmological constants separated by a brane. One would expect to see many interesting things there. These future directions are not limited to small c. Okay, this might be a good time to pause again for questions, because I'm going to switch to a rather different topic.
Hi, I have a question.
Sure.
So it seems like some of the strain tension is 0, right?
Yes.
Do you have any comments on that?
Like
you kind of have some tensionless brane, which is kind of
Yes, so the sigma brane seems to be transparent, and also we have this negative brane tensions. Well, okay, let me say this. So the negative tension branes are problematic if we think of them as fluctuating objects. The word volume scalar representing the transverse motion of the brane would have a negative kinetic term. The energy of the brane would be unbounded from below as the surface of the brane becomes arbitrarily rough. And the way to avoid this is to declare the brane not to be a fluctuating object, but just a fixed defect that carries energy density, which can deform the space-time around it. Examples of such defects are orbifolds in string theory, which are fixed planes of a symmetry projection that removes states from the spectrum odd under symmetry. It's quite common to require a Randall-Sundrum brane to be non-fluctuating orbifolds. So this is not an unreasonable solution. And for the zero tension brane, they could also in principle be fluctuating objects, but then self-consistency of the constructions seem to require to treat all the branes on an equal footing. And so we will just treat all branes as not fluctuating.
Okay, thanks.
Yeah, thanks for the question.
Excuse me,
Sure.
as I understood this kind of duality between ADS3 and this called Ising CFT, it's not like the other ADS CFT. I mean, the partition function of gravity part is not exactly equal to the partition function of the boundary part. Yes, right? So there is a proportionality between the partition functions. Yes. But this is not the problem. The problem which it's not a problem, just a question. Is it possible to calculate the entanglement entropy for this Ising CFT and then probe the gravity bulk theory through the Ryota-Koinagi proposal? Because we know Ryota-Koinagi proposal for entanglement entropy perfectly works in ADS3. So if you think that this duality is correct, then if you give me, for example, the holographic, the entanglement entropy for the boundary part, which in your case is Ising, so then if this duality really exists, then you have to find exactly the holographic entanglement entropy, or you have to find exactly the same bulk. It is possible to calculate the entanglement entropy here. In your knowledge for Ising?
Yeah, so the entanglement entropies for Ising CFT or Ising BCFT are known. The results are there. So if one wants, one can do the RT procedure and try to write down the entanglement entropy in the CFT side and compare it to the gravity side. But the problem may be that right now the partition function of the gravity is just the CFT partition function. It might not be obvious how to, for example, compute the minimal surface, etc. But that's definitely an interesting official direction to pursue. Yeah.
Thank you.
Hello, I have a quick question.
Sure.
I wanted to ask, actually, this is, sorry, the slide you were just on was a good slide for it. If you could go back a couple of
yeah, sure.
Sorry. I wanted to ask, right, this is perfect. I wanted to ask a question about the two cuts that you consider here. You consider the thermal ADS3 cut, which goes vertically through, and then you considered a BTZ black hole cut that goes this way. But of course, there's many other possible cuts that you could be building through your solid torus. How should I think of those?
Yes, so when there's no genuine boundary, there are the full SL2Z family of black holes. You can have rotations, etc. But when you have a boundary, so when you have a genuine boundary, two genuine boundaries, when you have a cylinder, we thought about this a little bit, but it was not obvious to us how one could incorporate this rotation. So if you do a twist to a cylinder, it's still a cylinder. It's not like after you do a twist, you identify the two boundaries, you have a different saddle. So so it seems to us that only these two solutions make sense. Okay, if we don't have further questions for now, maybe I can move on to the other topic, and we can come back to questions regarding the previous parts later after the talk. Let me, is this the correct slide? No, sorry, too much. Okay, so since I have additional time, I will advertise a few more slides on another related work. This is non-handle bodies in the case without general boundaries. So warnings that this part may involve more mathematics. We have mentioned that the asymptotic boundary of ADS3 can be of higher genus. And fixing a genus G, the gravitational partition function can be organized into a summation of various saddles X. Here, omega is the generalization of the modular parameter tau on higher genus. It's called a period matrix. It's G times G dimensional, complex valued, symmetric, and positive definite. And when G is larger than 1, some of the X are handle bodies, while some are not. Handle bodies are like higher genus generalizations of solid tori, where you fill the interior of the genus G surface by making all the meridians contractible. This is the most trivial filling of genus G surface you can think of. And as for non-handle bodies, if you look for an intuitive picture, you will find none. There are still three-dimensional manifolds with genus G surfaces as boundaries and can potentially be the solution to Einstein's equations, but it is really hard to imagine them. And here is an attempt. The shadowed regions are 3D interiors. So this non-handle body is constructed from a 3-manifold with 2 separate boundaries of genus 2. One then do some kind of Z2 quotient that involves the identification of the 2 separate boundaries together with an orientation reversing fixed point free reinvolution, such that this resultant manifold contains no singularities. These type of non-handle bodies are called twisted eye bundles. And this is already the simplest case when confined for non-handle bodies. So now you may have a feeling of why non-handle bodies have been quite a pain to study. They're not intuitive, there's no systematic construction, and the mathematics is heavy. And actually, if you search on Google for non-handle body, there are only 36 results. And so 35 of these papers are not really focusing on non-handle bodies, except one. And that one important paper was by Xi, who did a rough classification of the non-handle body solutions to the ADS3 gravity. Wrote down the abstract formula relating the partition functions of non-handle bodies to the correlators and partition functions of more elementary non-handle bodies. However, the formula were too abstract to be applicable, and the constraints were strong, such that many non-handle body solutions were not included. So it was also argued by Yin that the semi-classical contributions from non-handle bodies should be sublety compared to handle bodies. And this was confirmed, again, semi-classically for the specific class of twisted eye bundles numerically. So what we are curious about is whether there is a more general treatment to non-handle bodies and what will happen in a strongly coupled quantum regime and whether non-handle bodies are really sublety. Most of the people in our collaboration, including myself, are from backgrounds of topological physics, topological quantum field theory, and mathematics. So we will again take a topological point of view of the problem. We will not have full answers to these questions, but will hopefully provide a way towards the answers and stimulate more discussions. We start by the description of non-handle bodies. The tool would be dense surgeries. I will review this concept later, but before that, let me tell you the main idea of the description. There is a powerful mathematical theorem, Licorice-Wallace theorem, saying that any closed nice 3-manifold can be obtained by performing a dense surgery along a framed link inside 3-sphere. There's also a Fork-Law theorem, which is a generalized version of the Licorice-Wallace theorem, saying that any orientable connected compact 3-manifold with a genus G boundary can be obtained by a dense surgery on a framed link inside the genus G handle body. With this theorem, one can thus use different framed links to enumerate all 3-manifolds with genus G boundaries, including non-handle bodies, but modulo an equivalence condition called the Kirby moves. Let me give some intuitive definition of the relative concepts. So the first one would be a knot, which is topologically just a circle and can be embedded in the 3D Euclidean space in a weird way. These are some examples. And the link is a set of knots linked together or knotted together. And here are several examples. And giving a link a frame means to thicken the circles such that the self-twistings become visible. In other words, these two configurations were indistinguishable for unframed links, but become distinguishable when there's a thickness. Now, a dense surgery is a way to generate new manifolds from old ones. This procedure is roughly to drill a tubular neighborhood of a frame link from an old manifold. Say the frame link has n components, namely n knots. Then after drilling, the remaining manifold would have n boundaries, n components of boundaries, and each of them is a two-dimensional torus corresponding to one component in the link. And next, one takes n solid tori, which also have n component of two-dimensional tori as boundaries. One then glue the drilled manifold with this solid tori along their boundaries by a homomorphism. And finally, the extended curving moves are three moves that can relate different links that live inside the same manifold, which has a boundary of genus G surface. One can add, for example, one can add an unknot like this and slide the knot over handles, or cancel the two knots linked in this way. So these are the three extended curving moves. But the details of these moves or dense surgery will not matter here, as I will not show you any details. Next, using this concept and the generalized Licorice-Wallace theorem, we will present the description of twisted eye bundle using surgery. To start with, I will review a construction of twisted eye bundles. We start from a hyperbolic three manifold with two boundaries of genus G. The metric looks like follows, with ds squared sigma g being the metric with constant negative curvature on the genus G surface. So this system is just a genus G surface times an interval. The metric has two asymptotic boundaries living at r equals plus minus infinity. Our target is the twisted eye bundle, with just the one asymptotic boundary. So naively, one just to do an identification of r equals negative r. But that will generate an orbifold singularity at r equals 0. To resolve this, we do a Z2 quotient that is a composition of this parity r going to negative r and the fixed point free involution of the genus G surface. Involution means the action squares to identity, and the requirement of fixed point free makes sure that the resultant manifold is smooth. In other words, at r equals 0, the manifold is sigma G quotient I. It's smooth, there's no orbifold singularity. And such a fixed point free involution always exists for G larger than 1. Okay, so the resultant manifold then contains no contractible cycles inside the three-dimensional bulk. Compared with the handle bodies of genus G, which always have G contractible cycles, this twisted eye bundle is really as different as it can be from the handle bodies. And actually, twisted eye bundles were argued to be the only class of elementary non-handle bodies relevant to ADS3. We're not sure about this, but this means twisted eye bundles compress a set of very important representatives of non-handle bodies.
What is the definition of the term elementary in this case?
Oh, so, okay, yeah, this follows from the construction in a paper by Ying. His classification of non-handle bodies is like that. He has a procedure of reducing a general handle body to elementary non-handle bodies using a few moves. And then and he was able to provide an abstract equation for twisted eye bundles, which is the only relevant elementary non-handle bodies.
Okay. All right, thank you.
Sure. Okay.
Excuse me, such
sure.
hyperbolic three manifold with genus G, they are solutions of the Einstein gravity, or
yes?
From where these geometries come? I mean, they are
yes.
exact solution.
Yes. So this metric is a solution of Einstein's equation. So okay, all solutions of Einstein's equation in a Euclidean signature can be obtained from a quotient of the trivial ADS3 by some subgroup of the Kleinian group. And for this metric, the group we use is the Fuchsian group. So, well, in short, yes, these are the solution of Einstein's equation.
But with singular curvature R, I mean, I guess you have a genus G. As so the number of the genus G, so you have a singularities for the curvature. Yes, something like that. I just want to imagine this.
So in 3D, so let's go back to the genus 1 case. Even in genus 1, for the BTZ black hole, there's no curvature singularity anywhere. So in 3D, there's just no curvature singularities.
Thank you.
Okay, so now let's try to understand how to understand these twisted eye bundles using surgery. We were able to find the following framed links that relate genus G handle bodies to twisted eye bundles with the same genus. It turns out that even genus and odd genus should be treated separately. These figures are not possible to be understood in real time. I just showed them to you to let you know that finding these links is possible. The simplest case of genus 2 is also shown here. The framed link is the blue curve and the framing is -2. The homomorphism for the gluing procedure is computable. I should note that the surgery is not unique. There can be different links that are related to each other by curbing moves, which can all give the same topology of twisted eye bundle. Yeah, the previous slides are actually more or less the main result of our work regarding non-handle bodies. That is the enumeration of non-handle bodies using surgeries. But one can try harder to use this surgery data to compute the partition function of twisted eye bundles, but these will be based on more assumptions. First, we will assume that the partition function behaves in the same way as TQF topological quantum field theory partition functions under surgeries. This is a natural assumption in the sense that we expect the system to be topological, but it's still not a very solid assumption. In TQFT, the partition function of a weird manifold like a twisted eye bundle can be computed in the following way. First, one color the link, this blue link, for example, by something called a Kirby color, which is a certain combination of admissible colors in the TQFT. For example, for Ising TQFT, the admissible colors are just one sigma inside, and Kirby color is some combination of this. And then one uses local moves such as braiding and recoupling to resolve this complicated link diagram into something simpler, that is the fusion diagram. These fusion diagrams form a basis of diagrams in the handle body, so it's always possible to do this simplification of the link diagram into fusion diagrams. And then the partition function corresponding to each fusion diagram is just the characters of various conformal blocks in the corresponding CFT. So this procedure gives a way to compute the partition function on non-handle bodies, express them in terms of partition functions on handle bodies, modulo the subtlety that the surgery is not unique because the equivalence condition due to Kirby moves mentioned in the previous slide. Equivalent surgeries may give different resulting partition functions. So one reasonable treatment is to use the simplest surgery, but in generic cases, it's hard to define what simple means, and it's suspicious that the simplest surgery would give the most correct answer. So in one sentence, there's no canonical choice of surgery and thus no canonical expression for the partition function using surgery. But if one chooses to use the simplest surgery diagram at genus 2 in the previous slide, then at Brown new central charge equals 1/2, one can compute the partition function of the twisted eye bundle to be chi-vac norm squared, where chi-vac is related to the CFT conformal blocks in the following way. So each chi square bracket here can be expressed using Siegel theta functions. So it's a abstract, it's some explicit formula. And this partition function of chi-vac norm squared is a summand in the full gravity partition function. The full partition function contains two summations. One is over topology, for example, when you have handle bodies and different non-handle bodies, etc. Another is over geometries, which is summation over SOMO ADS3 and the BDZ black holes in the genus 1 case. And on genus 2, this modular sum is over plus group of genus 2 surface, and the result is 96 times the Ising CFT partition function on genus 2. Because of the fact that there is no canonical choice of surgery, it's hard to make sense of this number 96 here. But it can be shown that where we use a different surgery diagram, the result of this modular sum will still be a number times the Ising CFT partition function, which is good enough to support the duality. Okay, finally, let me summarize on the non-handle body part. So we have a general formalism to enumerate the handle bodies. We're able to compute the partition functions under certain assumptions. And there are some, in the case of twisted eye bundle, C equals 1/2, we can show that the gravity partition function is proportional to the Ising CFT partition function, and the twisted eye bundle contribution is not necessarily subleading. But there are unresolved issues. The first one is that we don't know how to sum over the topology. There is a huge number of framed links that can live in a handle body. Performing the surgeries with respect to these different links can thus lead to a huge number of different topologies. It's not obvious how one should sum over them and what are the weights for each topology. And the second one is, as mentioned, there are many different surgeries and can give the same non-handle body, and there's no canonical choice. So as a summary, we have found something exciting, but there are still a lot of things to be done. And hopefully this will stimulate more discussions, and maybe one of you already knows how to resolve these issues. Yeah, thank you. This is the end of my talk.
Thank you very much. That was a wonderful talk, very interesting material. Everyone, please thank our speaker in either virtually or in real by unmuting. And we can have some more questions, I think.
So I have a question. So maybe you mentioned it and I missed it. So are there circumstances in which non-handle body actually shows up in the holographic dual correspondence?
So if I'm understanding, I'm not sure if I understand your question correctly. So the full gravitational partition function should include summation over all, even semi-classically, it should include all saddles of Einstein's equation, all solutions of Einstein's equation, and non-handle bodies can also be solutions to Einstein's equation. So we have to sum
yes,
over them.
I think I understand that. So that's a requirement from the gravitational point of view.
Yes.
So my question was that, are there any known holographic correspondence of that to CFT in which CFT calculation compares you to sum over non-handle bodies as well?
Oh, not that I know of.
Yeah, so there is some puzzle about that. For example, in the paper last June by Maroni and Witten and also the Cornell group, they considered higher genus partition function ensemble average, and they found that the result can be interpreted just as sum over handle bodies. So if the gravity theory in the dual sums over hyperbolic geometry, there seems to be missing the non-handle body geometry. So
I see.
I found
So
it very confusing.
So in our case, for example, the contribution for higher genus handle bodies. So let's take genus 2, for example. In my case, the genus 2 summation over handle bodies give me 384 times the Ising CFT, while the twisted I bundle give me 96 times the Ising CFT. But they are both Ising CFTs.
Oh,
so
they are proportional to each other.
Yeah, so it's hard to distinguish the contribution is from which saddles, which topology. I'm not sure if it's the same as in their computation. So.
Okay, thank you.
Feel free to unmute yourself and ask a question if anyone has one. Okay, well, let's thank Zhu-Xi one more time.
Thank you.
I recommend that people, again, apologies, we can't offer you lunch or anything in this way, but recommend that people have a break, maybe get some lunch. And let me remind you again to join the gather space. I'll leave the links up. Again, you can look in the chat to get the link and the password. And also, I'll put a screen up to remind you need to download Chrome. But I really recommend it. People have been using it to chat, whether it be over lunch or what have you. So see you there, perhaps. And we will reconvene an hour from now for the next talk. I'll leave the Zoom open as well. Thanks, everyone.